missing research at our lab here every year for 3 months. So John,
yeah, okay. Let's move to the first one. This is the general outline of the talk. I'm going to start off talking about complexity and what it means. Then I'm going to move on to talk about organization, and then finally about emergence. And on the way, I'll be talking about hierarchies. This is all pretty theoretical. That's what I do. I'm an analytic philosopher. I analyze things. First of all, defining complexity. There are a lot of people who argue that complexity is an observer-dependent thing. There's some truth to that, in the sense that what we observe will, and what scale we observe it at, will give us different values of complexity. But that doesn't mean that there isn't intrinsic complexity within the systems. The observer dependence depends to some extent on scale dependency. Also, there's a confusion. There tends to be a confusion between complicated and complex. Complex systems are usually discussed in terms of complex organization. We'll get to that later on when I discuss organization. There are mathematical notions, and eventually, like I say, I'll get to complex organization. It's prevalent in systems theory in particular, this idea that complexity is an observer-dependent thing. A lot of systems theorists go further than that and say we don't observe things, we only study the models that we have of things. Although it doesn't, to my mind, to have a model of something without there being something that's being modeled doesn't really make sense. I mean, we interact with things. We don't interact with models. We may think with models, but we don't interact with models. So there are some theories that are going to be better than others, even if all of our theories are models. And they're useful because of simplifying these assumptions that make them tractable, but they're also useful because they're accurate. And there's a bit of a tension between the two. It's nice to have simple models, but simple models tend to be inaccurate, especially when we're dealing with complex things. So there's some truth to the observer dependence notion, which is we choose our models depending on what our pragmatic values are. And we should be aware of this. What is a model? Well, I like Robert Rosen's modeling relation. It comes from Hertz originally. The basic idea is that we have a natural, including a man-made system like a social system or economic system, that we want to model. And this will have some causal structure. And then a model is a set of logical relations, and often called a structure in logic. Models in logic are just things that have a structure. Now, the natural system is going to have a causal structure. So an accurate model is going to be accurate in as much as its logical structure maps the causal structure of the intended systems. Maybe incompletely, or maybe only in some respects. but nonetheless there will be a correspondence between the two. And the nice thing about this way of thinking about the structure of the nature of the world is that, that we have the same sort of thing, a structure, in our minds and in the world that we're trying to model. And in fact, in other places I've written about a book we have called Everything Must Go. We argue for structuralism. We say the world is actually made up of structures. And consequently, we can comprehend the world completely because, in principle anyway, or any part of it, because we use exactly the same sort of thing to set up our theories as to what is the nature of the world, namely structures. Yeah, as I said, there's a sense in which we can only work with models, but this has been overemphasized. One thing, the world can surprise us, and if all we had were the models in our head to work with, then the world wouldn't surprise us. There must be something out there that's coming in that contradicts our models. So there's more than our models out there. I'm going into this this business of the nature of the observer and the observed to some extent because the view is so widespread that all we can really work with is our models. But that's not true. We interact with the world and the world can surprise us. And also this idea that the world can't really be understood by us because the world's a different sort of thing than what our thinking is. What I'm saying is our thinking has the same nature as the nature of the world. Okay, a couple of things on scale dependency. This is something that is observer dependent. We focus on a particular scale, and this is going to be dependent on our interests. Also, things can be simple at one scale, but not another. Well, just for example, we have very complicated molecular emotions, but relatively simple, at least at steady state, microscopic thermodynamic properties. So at the phenomenological thermodynamical level, things are relatively simple compared to what's going on underneath. Similarly, local molecular emotions versus the intermediate scale molecular emotions in genetic cells, which have a larger structure, and in some ways are more simple than the individual emotions. In fact, we can't calculate from the local molecular emotions what the intermediate scale emotions are. It's not a tractable problem. Now, for some particular interests, some scales are more appropriate than others. That doesn't mean that scale is arbitrary, though. If we have a particular interest, there will be particular scales that are useful to look at. That's not an arbitrary question. So the choice of scale isn't completely arbitrary. And we can make mistakes about the appropriate scale. I could give some examples, but they would take too long. The sort of mistakes we can make can be due to external conditions interacting in complex ways with internal conditions. Whereas we might assume that the system has particular laws which are independent of the boundary conditions. The boundary conditions may not be fixed. So to choose a particular scale, we might miss the nature of the changing boundary conditions. But more often it's some combination of the two. It turns out that these problems appear specifically when we have complexly organized systems, especially those that are emergent. Like bit got rid Getting back to complicated versus complex, complexity theory in some circles has come to mean something more than just complicated. The Santa Fe Institute is probably the best example of this. But there are other circles, like the New England Complex Systems Institute, where complexity just means complicated. And they tend to offer what I call simple solutions to complex problems. They say things like, a perspective that considers emergence is often contrasted with a reductionist perspective, with things about parts in isolation. Reductionism is often vilified anti-complex systems view of the world. The context of a system is based upon a limited form of reductionism that distinguishes the system from its environment and the parts of the system from each other. The key difference is that a non-reductionist approach considers the relationships among them. That is completely and utterly trivial. Yeah. And that's what they put forward and charge people a lot of money for. I mean, this is why I put it up there, because it's so silly. Mathematical complexity. There are ways to measure complexity mathematically. Actually, what we're measuring here is complicatedness. It can be the minimal amount of information that it takes to describe something. And this can be formalized as algorithmic complexity, which is the length of the shortest self-delimiting program that can produce something structured. It's basically the amount of information. It does depend on the programming language, but that's negligible for really complicated things. And also, if you're comparing the complexity of different things, the programming language part drops out. And like I say, it really corresponds to complicatedness. Here's a little model of how it works. We have information in a structure. We ask 20 questions, it's 20 questions sort of game, and we get answers of ones and zeros to the questions we ask, yes or no. And we just keep doing that until we exhaust all the things we've asked about this thing. It doesn't matter if some of the questions overlap, because what we do next is we use algorithmic information theory to compress the amount of information. So we get the amount of information that's in this in its shortest form. So there is a mathematics. It turns out this can't always be calculated, but it can for DNA, for example. It can for quite a few interesting things. But in principle, there's a finite amount of information in any system, and this can be defined. And we can make estimates. If we can't necessarily give the exact amount of information with a given system, we can make estimates using this model of how much information there is in a system, how much information there is in different systems. But like I say, for things like DNA, protein structures, we can calculate it exactly. Cliff Hooker and I distinguish 4 types of systems. Type 1, which are simple and low organization, planetary orbits, pendulous springs, sort of things you learn in the first year physics classes. They're type 2, they're complex with low organization, ideal gas, perhaps macroeconomics, biological populations as they're understood in biological population theory. They're type 3, which are simple with high organization, computer, military, Catholic Church, perhaps. And then finally there are type 4 systems, which are complex with high organization. These would be living systems and minds would be primary examples here. And obviously these are the ones we're interested in when we're dealing with biological systems. They're organized complexity. Not just complicated, but they're organized complexity. Here's a little model here. We've got organization going in this direction, and complexity going in this direction. This is a schematic. I wouldn't say these are scales, these are just directions. So what is organization? That's a nice question. The basic idea is that an organized system is interconnected in complex ways so that there are both local and non-local effects, so that there are interactions at a close scale, but also there are interactions at a larger scale. The system can be strictly hierarchical in some cases. The higher levels can be the sum of the effects of the parts, or it could be the behavior of the parts is strictly controlled from above in some sense. This sort of systems are decomposable, and they're not, I would say, complexly organized. Complex organization involves neither summation nor top-down control, but shows an interaction of both bottom-up effects and top-down effects. So we can't fully separate it into top-down or bottom-up composition, but we have to work from both sides. And they can't be decomposed, and then, like, atomistically. There are ways to measure organization. One is logical depth, due to Charles Bennett. The minimal computation time to produce the surface structure for a maximally compressed form. In other words, we have the information in the system. We want to produce the system. It's going to take a certain amount of computation effort to produce the surface structure from the bottom structure. The chairs in this room are fairly well organized, so it doesn't take a lot of computation time to calculate the organization of the chairs in the room from the amount of information that's required to describe their positions to begin with. There's another term called sophistication, is pseudo-outline. He calls this the number of logically simple steps required to produce a structure from its components. This is a more physical notion. He's a biologist. But you can see there's a similarity between these two. Exactly how they fit together, neither he nor I know. But I suspect they're closely related. And then finally, there's the notion of thermodynamic depth. This would be the minimal work required to produce a structure from its components. And again, this looks a little bit like Atlas sophistication, and also looks a little bit like logical depth. But it turns out there are some systems which Atlas pointed out are infinitely sophisticated. It would require an infinite number of logically simple steps to put it together. That means you can't compute the surface structure from the structure of the components. Those are relationships, non-computable. Also, there are cases in Bennett's case where the minimum computation time, or the minimum number of computational steps, is infinite. These are non-computable surface structures, basically. So there's no way in principle to compute the surface structure from the component structures. It turns out Bernard cells are one of these things. It's a really simple case, but it turns out that Bernard cells can't be computed that way. But thermodynamic depth is different, because obviously you can do a certain finite amount of work in order to produce a complex structure. So it turns out although the similarity between these, amongst these, is apparent, they're not really the same thing. And especially thermodynamic depth can't be the same thing. I guess so. this is a notion I introduced to deal with a species issue. Cohesion is the dynamical property that individuates something, whether a thing or a property, and it's grounded in the logical condition of identity. But it's going to be peculiar for each thing, so there's an empirical component to the notion. It requires dynamical closure, so we have a test of whether or not we've taken what we need into consideration by looking at the closure conditions. So the closure of the property of, say, you're probably aware that some birds will flap their wings like this as if it's broken when some predator approaches their nest, and they move away from the nest, and the predator sees, oh, there's an injured bird there, I'll go and chase after the injured bird. Now, what are the cohesion conditions for this property? Well, it's not for the benefit of the bird. You might say it's for the benefit of the eggs in the nest. That's not a bad idea, but actually it's a combination of the two. It's for the benefit of the lineage, and that's how it gets selected. So the cohesion property there, the cohesion of the property there, the closure conditions are for the lineage and not for any of the components. That's why looking at the closure conditions is important to see what the property is a property of. Okay, just relatively quickly, identity is a fairly simple notion. It's an equivalence relation. It doesn't really help us because in individuation, because the identity of everything is the same. Identity is the same property for everything. So one of my professors, John Perry, came up with what he called the unity relation, and it holds amongst parts of things if A and B are parts related, then A, U, B, the unity relation, and B, U, A. So it's symmetric. It's also transitive. And by these two, it's an equivalence relation. So anything that holds a unity relationship, if you take the closure of that, then you'll have what unifies all the parts of the thing into the same thing. The unity relationship of A, U at big A, will contain all and only the parts of A. It's a fairly simple logical notion, except that well, the unity of A for some things is completely nominal, like for sets. We just divide it in terms of its members. For some systems, this will apply as well. We can say a tree is a plant over 4 meters tall, so we get the unity for the measure aspect for a tree will include being over 4 meters tall. But the unity of some things is natural. It has some empirical and testable aspect. An extreme case is a quartz crystal. These parts and interactions have to be discovered. A dynamical system is a set of interacting components that's characterized and individuated by other systems by its dynamical interactions. And gold, what makes gold gold is atomic number 79. We know that now. People in the past didn't know that, but they were still talking about gold because it was this thing that had the atomic number 79. Why is this important? Well, it gives us a way of defining cohesion. If we assume dynamical realism, the view that everything is either dynamical, involves its forces or flows, or else can be understood in terms of dynamics, then in particular, all natural entities, objects, systems, properties, processes, are dynamical or abstractions from dynamical entities. Now, if we restrict ourselves to dynamical properties in the unity relation, then we get a dynamical unity relation, and that's just what I call cohesion. So this explains what cohesion is and why cohesion acts as an individuating property, because it's basically a unity relationship, which is an equivalence relationship, which tells us what it is to be a particular type, a particular thing. It gives us an identity conditions, essentially. It has some interesting characteristics. It comes in degrees, so we should expect intermediate cases. They can differ in strength in different dimensions, so we need a cohesion profile of an individuating object. Hard stacks are rare, but they can be fatal, for example. So they don't happen very often, but they can break up a person's cohesion. But it both unifies dynamical objects and dynamical objects. I could call this the dividing glue. So it's an effective criteria of individuation, but also being dynamical, it's testable. In fact, this is one of the advantages of dynamical realism, that it only allows things that we can actually interact with. There are none of these imaginary, virtual, whatever types of things that we can't interact with. But its real strength is the way it forces us to look at dynamical closure whenever we want to claim that something is individuated. And I mentioned the bird case. I think I'm going to skip through these because they're rather technical. Downward causation. I made this point briefly in a footnote in a paper in 1988. 1988, where I talked about downward causation, not seeming to get the ontology right. But it seems to me that downward causation is best explained in terms of cohesion. It is a large-scale property that confines the lower-level properties. It constrains them. So if you're familiar with Paul Humphrey's work, it's similar to Humphrey's fusion property. A natural hierarchy. Well, if it's natural, we're assuming dynamical realism, then hierarchies are formed by dynamical properties. They're not imaginary things. So any hierarchy has to have a hierarchy property that orders the hierarchy into levels. And the hierarchy property that has to exist at each level. Whatever it is that makes the hierarchy is going to have to apply across the levels. By dynamical realism, natural hierarchies must have a hierarchy property that's either dynamical or definable in dynamical terms. Dynamical hierarchies are determined by a part whole, where the parts and the wholes are each individuated by cohesion. So natural hierarchies are a cohesion hierarchy, basically. This is important. And the only point this makes is that I've noticed that there's a tendency to confuse class hierarchies with hierarchies in individual systems. And class hierarchies are abstractions. They may be grounded, the abstractions may be grounded in dynamical properties. But the real dynamical hierarchies are always going to apply to particular things, like, say, my body. Well, I might want to talk about the mental and the biological and the chemical and the physical. That's an abstraction. Mustn't be confused with the actual hierarchy that exists in some system. Okay, for dynamical hierarchies, all the levels have to be cohesive if they're dynamical, or else they wouldn't be naturally individuated. Since the levels are cohesive, the same basic properties, and principles I skipped over before are going to apply. Structural and process levels may coexist, and they generally do coexist, and this can cause some confusion. Process levels can occur across structural levels, like the respiratory process that occurs across the subcellular, multicellular organ and multi-organ levels, correlating subcellular activity with both pulmonary and cardiovascular activities, and conversely. So here we have various structures, and the actual hierarchy in this case cuts across those structures. The levels can be more or less transitory, especially in living things. So there's no simple picture of a system as a single series of universal permanent levels like the floors in a building. It's just not how biological systems work. It's not how any complexly organized hierarchical system works, in fact. But that's often the way they're described in books. That's often the way they're portrayed. It gives a nice, simple picture. And this is a case where the simplicity violates the accuracy condition that I was talking about before. Emergence. This is getting close to the end. Sometimes it's meant to be something that's really unexpected. We talk about the emergence of the internet, the emergence of a new scientific discipline, or the emergence of a new national party. But there's no implication of more than surprise. You might call this epistemic emergence. I wouldn't even go that far. I just think it's a surprising event. But this isn't the traditional philosophical notion of emergence. Mind you, it's used widely because emergence is a buzzword right now. So people like to use the word emergence. The philosophical notion goes back to Aristotle, but the concept, but without the name, appears in John Stuart Mill. It says a living body cannot be understood as a mere summing up of the separate notions of its components. The basic physical laws aren't violated, but new laws impose further restrictions. So we have the same thing that Bob was talking about. We've got no violation of the basic laws, but we've got something new appearing that wasn't there before. And it can have a law-like character. It needn't, but it quite often does. The word itself comes to the guy named Lewis, so I know almost nothing about. Said the emergence is incommensurable with its components and cannot be reduced to the sum of their differences. There's this very basic idea that emergent things aren't merely aggregates. C.D. Broad had the clearest notion. He talked about unpredictability, he talked about non-reducibility, he talked about holism, and he talked about novelty. That's the tricky one. There's no clear definition of it. It's not merely surprising. It's supposed to be a new kind of property, but exactly what's a new kind of property? And he wasn't very clear about that. Bernard cells, which I mentioned before, it's a model distributive system. I won't go through the details. Probably either you already understand them or my brief description here won't help a lot. But the fluid forms cycles once it passes a certain temperature and a certain gradient. And there's a very specific point at which that occurs. We can get the equations of motion. They didn't come up very well on this. I copied them from someplace else in another Microsoft program, but Microsoft is not self-compiled, unfortunately. But anyway, you can see from this mass that the equations are highly nonlinear. Nonlinearity is a characteristic of, it doesn't necessarily imply, but it's a characteristic of this sort of situation where you can't get reduction. Now, the interesting thing is the way to solve the equations of motion of the Bernard cell is to calculate the large-scale motion, and then calculate the molecular motion, and then find where the two equations meet. You can't do it by calculating the molecular motion and then deriving the cyclic motion. It just can't be done. It's mathematically impossible. It's well known that it's a mathematically impossible problem. So here's a case of working from the bottom up and from the top down to understand what's going on. Very simple case. Very simple case. And it happens in physics. And these things can happen in physics. You don't have to go to biology or to mental things or social things or whatever in order to get these sorts of problems. Intuitively, there are fluctuations in the density of the system. The fluctuations are larger the higher the temperature. There's also viscosity that creates cohesion amongst the molecules in the fluid. Or we don't even need to think of molecules, we can just think of the fluid as intrinsically cohesive. As the temperature gradient is increased, there are larger regions of greater and lesser density. These regions are either buoyant or the opposite, respectively. The viscosity of the fluid holds these regions together against their tendency to disperse thermodynamically. As the regions grow larger, this tendency overcomes the dispersive tendency, and the buoyant regions float upwards, whereas the dense regions sink. And because of the way that the experiments are set up, this results in very regular cycles of motion. So you can understand what's going on intuitively here, but you can't describe it mathematically from the bottom. There are ways to understand it, though, at least intuitively. Here's the definition of predictability. Again, this is rather technical, and I'm not going to go into the detail. But it applies to all closed Hamiltonian. By this I mean specifically energy conservative systems, including those without exact analytical solutions like the three-body case. We can predict that case for any period in the future we want to. Yeah, we can also do numerical calculations for any finite time. We can call this stepwise computability. Now, all computations are stepwise computable, but some don't terminate, as you may know if you've studied algebra. So, if we have a large enough computer, then we could, do the sort of Laplace's demon trick, apparently, and compute the next state of the universe from the knowledge of the current state in a stepwise way. And the macrostate of a microstate system can be predicted on similar grounds by doing a stepwise computation upwards. Okay, that makes it look like everything's going to be computable, just like Laplace's demon says. Not true. Not true. To undermine predictability, at least one of the systems has to go. And the assumptions are the system is closed, the system is Hamiltonian, and there are just sufficient computational resources. Now you can do quite a bit, even if these aren't completely satisfied. Laplace was able to show that the orbits of the major bodies in the solar system were stable for at least 100 million years. That's pretty good when they were calculating by hand. But what happens if some of these things go? In an interesting paper, Conrad and Suno point out that differential equations provide the major means of describing the dynamics of the physical system in both quantum and classical mechanics. This is standard. The success of this scheme suggests on the surface that the principle could be extended to a universal program covering all of nature. And a lot of people still think that. The problem is that the essence of a differential equation description is a separation of itself from its boundary conditions. And this is actually converging on things that Ron said. Boundary conditions being without arbitrary. But there can be a failure of independence. And this happens in what I call non-holonomic systems. Non-holonomic systems, the energy isn't conserved. This happens in dissipative systems. If you're looking, the energy is conserved overall, but if you're looking at the point of view of the system alone, then some of the energy is dissipated, it disappears. Under these conditions, the boundary conditions and system laws for the system itself can't be separated in principle. If the system's near holonomic, we can approximate at one end by step functions and at the other end by perturbation theory. And these are standard methods. The problem happens in the middle. And in the middle, I call these radically non-holonomic systems. That's where the problem lies. You can't approximate to standard compositional systems. These are exactly the systems that I call emergent. The dynamical conditions for emergence, the system must be non-holonomic, implying that the system is non-integrable. This ensures its non-reducibility because you can't solve the equations. Nothing can solve the equations. It's just the system itself, in a sense, solves the equations, but nothing outside of it can solve the equations. The system is energetically or information open. The boundary conditions themselves are going to be dynamic. I put in the condition the system has multiple attractors, but that might not be necessary. The characteristic rate of at least one property of the system is the same order as the rate of the non-holonomic constraint. That makes the whole system radically non-Hamiltonian. Especially if that property is an essential property of the system. In other words, part of what provides the system cohesion. That would make the whole system emergent, not just its properties. Some examples, quite surprising. I already mentioned Bernard cells, but the relationship between Mercury and the Sun is like that. I won't go into detail, it's a matter of time. Cell differentiation appears to work that way. Ant behavior works that way in many cases. Non-selective syntactic speciation appears to work that way, at least according to a model that I had a student make a number of years ago. So the examples are quite widespread. Notice I didn't mention organisms or ecosystems here at all. Those are the cases that I think would be very likely to have these emergent properties. So what you have is you've got at least two levels. You can't separate out the boundary conditions of the system from the dynamics of the system. They interact with each other. One way of putting it is the actual system does work on its boundary conditions, That work on the boundary conditions can lead to a greater organization of the boundary conditions, or it can lead to a degeneration of the boundary conditions, depending on the circumstances. But in either case, you can't predict the properties going to be emergent. I think that's all I have to say.
We have 10 minutes for discussion.
John, sorry, I don't know if I misunderstood something. I just would like to hear about non-holonomic constraint. What does it mean?
Holonomic constraints are ones that vary they're basically like if you have a field, then the field will be holonomic. The constraints of the field will be holonomic, and they vary only according to time for each location. But if they vary, if there's interaction between the spatial and temporal variation, then they may be non-holonomic typically. That's one way of describing it. Interestingly, the rotation of a tire is non-holonomic. And somebody said, well, you know, everybody knows about tires, but we don't think there's anything emergent going on. And I said, what happens when you get into the right situation and you go into a skid? That's an emergent phenomenon. That's an emergent phenomenon. You can control skids up to a point, but the exact point where the skid starts and what direction it goes is not typically controllable. One of the interesting things is when I'm talking about emergent structures here, it's not only that they're emergent in sort of abstract sense, so you can't do the reduction from the outside. It also means that it can't be controlled. It means it can't be controlled by anything, inside or outside. That it's, by its very nature, it's uncontrollable. Yeah, so another way of putting it is that the holonomic constraints is that they are energy conservative. So that's why I relate them to Hamiltonians. Now it turns out you can have non-conservative Hamiltonians, but in normal physics texts, the first thing they show you when they introduce the Hamiltonian is that they're going to restrict themselves to cases where the Hamiltonian has constant energy. So another way of thinking of non-holonomic constraints is ones that involve dissipative energy. All those are sort of equivalent at some level. I mean, they sound different, but physically they're quite equivalent to each other, to the best of my knowledge anyway.
Real quickly, properties is the fall of an apple, Newtonian. As an example, the idea is that fall of an apple is gravity. Everybody, well, that's it. But the actual timing of the fall of the apple depends upon the condition of the stem, the humidity, the wind, and so forth, and that can't be controlled.
Yeah, so right. Interestingly, when you look at the physics of a coin toss, I used to have a big American silver dollar, and I practiced and practiced and practiced. And I could toss it and have it come up the way I wanted to. It was big enough and heavy enough to overcome the effects of the air flow around it. But with a smaller coin, the airflow is going to have non-linear interactions with the movement of the coin, and you're not going to be able to control it, and consequently the average coin toss is a fair coin toss because of that. Yeah, it's very similar to the apple, because the apple's going to be hanging there in the wind, it's got the weather around it, it's got all kinds of things like that. It's more than just contingency. This is where I might disagree with you. It's more than just contingency. It's contingency in a way that really does involve objective chance. It can't be predicted. It can't be. It's not. Well, of course, you can always pluck an apple. But in a lot of these phenomena, you couldn't control it because they're not with small control movements. And I mean, the nature of control typically is to use small amounts of energy to slightly deviate things to go in a different direction. That's the sort of thing you can't do.
Interested in the cohesion. You state somewhere in your talk that cohesion is a property that individuates other properties. Is that?
Sorry, it's a property that.
It's a property, and which makes the individual.
An individual, basically, yeah. It's what holds the parts together, essentially, yeah.
What's the difference between this and connectivity between system parts?
There's
or
not really
between
any
mutual
difference.
information?
Just the connection among system parts would be a form of cohesion.
It is.
It would be a form of cohesion. Yeah, cohesion is a very general notion. It can apply to quartz crystals. It can apply to the container or gases in. It can apply to a network, that's held together by carbon transfer. It could be, quite a few things. Now, in a lot of cases, cohesion is reducible. I mean, I'm not saying cohesion is not reducible. In many cases, it is. But there are cases where it isn't. And the sort of non-holonomic constraint condition is the sort of case where it's not going to be reducible. You can only treat it holistically. Although you can measure the way the parts are interacting with each other and the strength of the interaction of the parts, and the value of that might tell you about the stability of the whole. In fact, it probably does. Almost certainly does. Yeah, but cohesion itself can definitely be reducible.
And about the relationship between complexity and organization, you say that there is organization in one level, I can measure. I'm just talking to see if I understood correctly.
Right.
The organization is one level, and we have one level below, one level up, and a complex system, and this level would be a system which the explanation of these organizations must take into account bottom-up and top-down.
Well, no, actually, it need only involve two levels. And organization can exist without there necessarily being what we call complex organization. You can have organization that's reducible as well. The organization that's reducible would be the type where everything's determined from the top down. Say, a parody of the Catholic Church, where the Pope gives commands, and the commands are followed all the way down. Okay, so he determines everything. And that's the opposite form would be where you've got, say, a salt crystal, where you've got ionic bonds amongst the atoms, and the combination of the ionic bonds is sufficient to explain the structure of the salt crystal. I deliberately chose ionic bonds because I suspect that covalent bonds aren't reducible in that sense.
I'd like to ask something. Your notion of cohesion kinds of competes for the same ground of a very popular notion, which is the notion of autopoiesis. But I agree with you that autopoiesis is a strange notion. It's a bit too closed. So I'd like to ask you to elaborate on your idea of interactive closure of processes. I think it has to do with cohesion and makes us be able to individuate a system which is much more open than Maturana and Varela's idea of autopoiesis, which I really don't get, because they say you have this closed system here, you have the environment, and they have this strange idea of a drift, that somehow the closed system drifts with the environment. I really don't understand what they're talking about.
I didn't go into autonomy. Autonomy is a special type of cohesion. which is based on organization, in which the organization provides the closure that is the cohesion. Now that's very close to autopoiesis. It's closer than just cohesion itself is.
Yeah.
That's close to cohesion, except the autopoiesis is closed to it's closed in a very special way. They sometimes talk about it as close to information. They sometimes talk about it as close to what's the word I'm looking for? Well, basically effective processes. Whereas in cohesion, as I understand it, there's a balance between the there's a balance towards the centripetal, but there can also be centrifugal forces, and there can so it's a matter of degree, and it's also open. There's no reason for it to be close to information. There's no reason for it to be close to anything. There's no reason for it to be close to efficient causation, just so long as the balance is in favor of the centripetal.
So for instance, if
So that's a major
the nodes of
difference
the
between-
network are exchanging more
Yeah.
information inside, they get information from outside, but the flow of information inside is much larger. So we
Yeah,
can
well,
see that.
On the autopoiesis view, the only information that can come in is stuff that is information that the system is already prepared for. So be prepared for it just means it's not new information.
Doesn't make any
Whereas
sense at
on
all.
my account, it's quite possible for a system to be affected by new information. It's going to respond to it in certain ways. I didn't go into that here either. But in fact, it's going to respond in such a way as to try to preserve itself. So it can actually adapt to the new information. So the autonomy on my account can respond to new information by adapting to it essentially. And I use this as a model for Jean Piaget's adaptation process, where he talks about assimilation and accommodation. Whereas I don't see any room for that in the Natran and Umbrella account. I see no room whatsoever for it
Very
in
strange.
Rosen's account. And that's what I see as a major flaw of both those accounts. I've got a couple of papers on that I've written, trying to make the distinction. The thing is that a lot of people have started using the word autopoiesis in the way that I use autonomy, and not in the way that people like Natran and Varela use their term. But I'm quite certain that my characterization of their terminology is right. For them, the environment of an organism is completely determined by its what could be called its Weltanschauung, but basically determined by its autopoiesis. Whereas for me, with autonomy, the environment can affect the organism in ways that it's not prepared for, but nonetheless can adapt to, because it finds new ways of adapting based on the very impulse that it gets into it from the environment. So the environment's more open, on my view. It's not part of the organism, so to speak, whereas it is for Natran and Varela. And I suspect it has to be for Rosen as well.
Well,
Well,
time to, okay.
real quickly, you mentioned logical structure versus causal structure.
Oh, yeah, right.
You seem to feel that there was no disparity here. We all know, of course, that Aristotelian causality runs the problem with loops and whatnot, but then there are other types of logical structures
Yeah,
besides
sure.
Aristotelian. There's this fellow by the name of Joseph Brenner who put out this book called Logic and Reality, I think.
Yes, I'm familiar with
And
this work. I
again,
don't
let me see if I understand it, and you can comment on it. I think what he's saying is that you take all these logics together, and they're really not sufficient for the way the world comes at us. That there is a sui propria logic and reality that we need to find that we don't already have, and you're saying essentially that's not true.
Yeah, basically I'm saying that's not true.
Why?
Well, the main reason is because our best theory of physics right now implies structure, that the world is actually based on structures.
Mm-hmm.
This is not a new view. This is what Bertrand Russell thought.
Mm-hmm.
Now, if somebody can find a good argument against that, then I'd certainly consider it. But right at the moment, that's my view. So we don't believe like there are Kantian things in themselves that are mysterious to us,
Mm-hmm.
or that there are underlying things or another that have some sort of being that is just inaccessible to us. Howard Patty believes that.
Believes what, that they're inaccessible?
Yeah, right. Howard Patty believes that, and it's been discussed on the biosemiotics
Yeah.
group recently. I haven't been able to prepare my answer to him yet.
Mm-hmm.
His basis for believing that, I don't know. It's just that he believes in this thing he calls the epistemic cut,
Yeah.
which is some sort of division between the way we think about things and the things themselves.
Right.
And I'm saying our book, Everything Must Go, which is based on structural realism, my dynamical realism is even more restrictive because it involves only things that we can in principle interact with. Says that, no, our best theory of physics says that there's nothing more than structure, and that we have access to structure. So there isn't something mysterious out there. Now, okay, maybe there is in some sense of his that we can never understand. What's the point of thinking about that? You know? I mean, seriously. There's enough mystery in the world just the way it is. At any rate, I'm not that familiar with Joseph's stuff.
I haven't read it either. Yeah.
I'm reviewing the paper right now, actually, for Foundations of Physics, and I'll be looking at it more carefully. At one point, he was talking about doing a second PhD. He got a PhD in chemistry. He was talking about doing a second PhD in philosophy with me. And until he found out how much it cost for a foreigner to study it in South Africa. So yeah, we know each other fairly well. But I couldn't really recite the principles of his logic and reality.
Okay, so we are on time. We can have now a break.